Hello, I'm Mark, and welcome to my Unreal Engine tutorials on how to add wheeled systems to our physics simulation components. So in this video, I think we're coming down to the final two videos, and in this video, we're going to be focusing on suspension systems. So in previous videos, we were able to create a engine simulation, which can allow us to take the accelerator input and turn that into vehicle torque. We created a transmission system to take that engine torque and convert it into angular position and angular velocity. Then we also went and created a steering system that we could then use to turn our wheels left and right so we can steer. And then I think in the final two videos, we went ahead and took a little bit of a detour, and I think it's a necessary detour, so that we could set up for to pipe out the simulation data so that we could use it within vehicle animations. So now I think we're in a good position to start bringing it home in the next two videos. So this video will be focusing on suspension, as seen here. And then hopefully in the next video, we'll be able to finish it off with wheel friction, which will then get us a full solution so that we can create wheeled vehicles that can drive across the surface of a map. All right, so as always, we have a lot of ground and a lot of code to cover. So let's get started. Okay, so I think the place we're going to start off is within our wheel simulation setup file. And as you can see here, we've been slowly stubbing out some of these structures as we've been kind of running into them through the various subsystems. So we have our wheel simulation set up here, and we'll get back into this a lot more in the next video when we start getting into wheel friction and how we're going to translate that angular velocity into and friction into thrust on the wheels. So we'll get back to that. But then we also did this suspension simulation setup too, and we kind of needed this a little bit for when we started getting into the animation, when we went and touched on the animation. So we've stubbed a little bit of this out. So I think with the in regards to suspension, we're going to go ahead and finish this all off. So we'll have all of the pieces that we need in order to simulate some kind of a suspension system, whether it be a spring, a leaf spring, or a core spring. We'll be able to kind of simulate that for each wheel on our vehicle. All right, so first off, we're going to need some supporting structures for our suspension simulation setup. So the first one is going to be, I'm just going to bring this over from the other solution. And I'll put a little space there. So the first one is actually going to be a copy and paste. So this is actually going to be our simulation suspension trace. So the way that this is going to work is that we need to use a tracing algorithm, right? And so we're going to either be using a raycast or a spherecast, right, in order to determine whether our wheels are on the ground or not. And so that's kind of what, and so we've got some supporting structures here so that we can figure out how far that cast at that suspension or that raycast or that spherecast is going to go down in order for us to be able to detect whether our wheel is actually touching the surface or if it's off the surface, and that's going to then going to do two things. One, it's going to be determining where we need to move our suspension system based on the springs simulation, right? And also that information is also going to be used in our wheel friction setup as well to determine whether our wheel is going to be free spinning or whether it's going to be getting traction on the ground. So we've got the suspension simulation tracing here. And then we also have a couple of other supporting enums. And we'll also bring in this other structure as well. So I'm just going to bring all of it in. So, and we need to get that API name changed over. Okay, so as you can see here, so we've got the suspension simulation trace. So this is going to be the start and the end. So this is, the start is usually going to be where our wheel rotation point is, right? And then the trace is going to be how far down the wheel. Actually, no, the starting should actually be the wheel, the resting position or the position of the center of the wheel based on the limits of the suspension system, right? And then the end trace should be how far out of the wheel, you know, how far down it's going to go to determine whether we're going to be hitting ground or not. So that's the start and the end. We've got to get trace direction as well as get a length. So we'll add these two functions in. We also have two types of sweeps that we'll be able to support. Raycast is the fastest, right? So this is usually what you might want to use. But I'm also going to add in Spherecast too. This is just, so Raycast is just a line trace, so that's just going to go down. Whereas Spherecast will give us a bit more volume if you find that you need to kind of do that. But what I'm using on that vehicle right now is actually a Raycast, and it's looking pretty good. Spherecast, does have a couple of little quirks because it's going to be a sphere and a capsule that you're going to be creating. But it's there if you want to use it. It is a little bit more intense than the Raycast, but again, it all depends on what you're trying to do. And then you've got the trace sweep types. So we've got simple, sweep, and complex. Again, if you need a simple, you can set it to simple. If you need a complex, you can set it to complex. It's up to you. And then finally, we've got these trace parameters. These are the parameters that are going to be passed to the simulation. So once you've selected whether you're going to be doing a Raycast or a Spherecast or a simple versus a complex, this gets passed in so that the suspension tracing will be able to configure itself for what you need. All right, so let's go ahead and get this function out of the way, or we'll get both of these functions out of the way. So I'm just going to say get potential fix. As you can see here, we already have another function here, which is part of the suspension simulation setup. I'm going to move this above that for now. I'm trying to keep things a bit more organized. Give definition. So for this one, this is just getting the direction. So let's bring this one over. Again, it's going to run direction end trace start and then direction dot vector dot get safe normal. So we're just creating a vector called direction. We're going to put the end trace minus the start trace, and then what we're going to do is get the direction, and off that vector we're just going to get the safe normal of what that vector is. And then for the length, it's a similar function. Let's see what we're going to do. I'm just going to copy this over. Suspension length is the same idea. We're just going to create a vector called direction. It's got end trace, start trace, end trace minus start trace, and then we're just going to take the direction, and then there's a function on there which is going to get the size, and then that will get the actual length if you need the length of the trace. Alright, so that's that. Those two functions are set. I'm just going to go and minimize our enums to get us some real estate. Alright, so that should be everything that we need there for supporting our suspension and suspension tracing. So next up, we are going to go and we should be able to come into suspension object here or struct here and start filling out all the rest of the parameters and functions that we're kind of missing here. Okay, so for the parameters that we already have, right, we already have the suspension axis. This is the local axis direction for, and this is for our suspension for force raycast traces. We also have the offset, so this is going to be the relative position. So if we need to add any more offsetting based on the position of the wheel, we can set that. I'm just setting this to 0 vector right now by default. We have a hard stop stiffness. This parameter is going to be relevant only when we're using Unreal Engine's suspension constraint, physics constraint, and they actually have one baked into the engine, and we'll take a look at that. But then suspension, this is the suspension max rise, and then we have the suspension max drop. Right now these are kind of even, but this is going to be the amount of, so the drop is the amount of tension, and this is how far the suspension can move beyond rest in the down position, right? And then you've got max rise, which is compression, right? This is the amount of distance that the spring, your suspensions can be compressed going from the resting position back up. So now that we've got those variables out of the way, let's go ahead and add the other two missing variables that we need to calculate our spring. And that is going to be our spring rate, which is going to be this is our constant, and then we have our preload. And so the spring rate, this is our constant, and this is a variable which we can, this kind of gives us kind of like that stiffness, where the spring preload is the amount of spring force, and this is independent of movement. So this is kind of like the stiffness that we're going to be using for movement, and this is going to be the force, which is independent. So if we're kind of rested out, right, then this is kind of where the vehicle is going to be kind of holding off on preload. All right. After that, now we are going to add some additional variables that kind of help to kind of smooth this out a bit. And make for a better, a more smoother spring simulation. So the next variable is going to be our damping ratio, and this is a ratio between 0 and 1. So this is how much damping we want to put into the spring. So this is going to help to kind of determine how, eventually we want the spring to get to a point where it starts to rest out, right? So if it's 1, it's going to be very, 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 very stiff, which means it's going to it'll dampen out pretty quick, where if it's like 0, you're going to see a lot more bounce, and it's going to take a lot longer for the vehicle to get to a point where it's not bouncing around on the suspension if you're not moving. Next up is going to be our wheel load ratio. Gonna just bring that in. And the wheel load ratio is just a value. It's a value again between 0 and 1. As you can see here, I've got the clamp in there. And what this is going to do is it's going to determine how much weight transfer is going to be on the wheel. On a particular suspension for that wheel. So that's kind of the wheel load ratio. Then we also have the raycast safety margin. So this is something that we can add to our raycast or spherecast, right? So if we're building wheels, we may need to add a little bit extra onto that calculation. So the raycast is going to take the size of the wheel and it's going to determine the length that it needs to trace. But if we need to add a little bit of a safety margin or a buffer in there, we can go ahead and do that through the raycast safety margin. And let's just put a default in there. So the safety margin right now could just by EAP set to 0. We don't really need to add too much of a safety margin in there. And then finally, suspension smoothing. So like anything, right, where we're trying to go between two values, and this is really more for the animation, but then as you're going to see, the animation kind of plays back into the simulation. So we're going to say we want to move here, but we don't want to go there too quickly, otherwise the suspension's going to look kind of very jerky. So we can use suspension smoothing to kind of try and smooth out the suspension so it's a bit more flowing and less jerky. But again, and these are again all things that we can tweak, and this is something where again you've got a minimum clamp and a maximum, go from 0 to 10 on your smoothing scale. And then finally, let's bring in our enums. Okay, and so here by default, I'm just going to set this to a simple sweep, and by default, I'm just going to set it to raycast. So this is simple sweeps, this is raycast, and so on. And we're going to be doing so the raycasts are going to be done on each wheel on each physics tick, since we're going to be doing this in the physics loop. So what it's going to do is it's going to go ahead, and that's what we're going to be using to keep the vehicle from sinking into the ground and into the dirt. All right, so now that we've got all of, so these are all the parameters that we can set within our simulation. So now let's go ahead and move over to our functions. Okay, so the first new function we need to add, I'm just going to go bring this over, is going to be our set suspension length. So this is a function that we need to, so what we're going to do is when we need to set our suspension length, the actual suspension length, we need to know what the length is going to be as well as the wheel radius. So we're going to do a calculation, and then that's going to set the actual suspension length. So we're going to be, so we don't just set it here, we can actually calculate that off the wheel radius. So again, as you can see, wheels and suspension, they kind of work together. So we'll be filling in some of these missing pieces as we go. We're also going to need the set local velocity function. So, and this is going to be setting a local velocity, which we'll be adding into the private section. So just ignore the red squiggly for now, but we'll go ahead and put those in. So that's the set local velocity, so we need to be able to set that. We have the local resting position, which is right here. So we have the get local resting position, so this is our local offset, but we also want to have a way of setting it as well. And that's the resting position is going to be the starting point for our simulation. So when we go ahead and create the wheel setup, we'll need to know exactly where we want to start the spring simulation. So this is going to be setting it, and then we're going to need to be able to get that information when we need to output it. Let's see, we have a update world raycast location. So this is a simulation that is going to be constantly moving. I'm just going to go and put all the updates in one place, and we'll put all the gets in the others. So this is an update world raycast location. So again, this is a simulation that is going to be constantly moving as the position of the wheel is going to be moving. So once we move the wheel, we need to update the raycast position so that it can continue to get an accurate line trace of where the wheel is in relationship to the ground. And then we also need to, okay, now we're coming back into our getters. So that should do it for the setters. So as for getters, we're going to need the get spring length. So there's our spring length. So we'll go ahead and fill that out. But that is going to be the length of the actual spring. And then we have the get suspensions force. And again, this is going to be an internal variable, so local velocity and in suspension force. These are variables that are going to be tracked during the simulation. And so I think what we'll do is once we get through these and up to the simulation function, I'll go ahead and add all the local variables that we need to be tracking. And then we have the get suspension offset, which is the max rise plus the spring length, which we'll be calculating in just very shortly. That's the offset. Then I think the only thing we're really missing here is the resting position. So we are setting the resting position, so this should allow us to get the local resting position. So this is getting the resting position. This is going to be getting the local resting position. So actually, no, we're just duplicating that function. We already have it. My mistake. Don't need that. All right, and then I've got another function down here, which is our simulate. I'm just going to put that there real quick. So everything has to be done through delta time. All right, so there's a lot of other functions I want to add, but before I get to those, what I'm going to do is I'm going to go ahead and add the private variables next. So all of these private variables are what we're going to be kind of calculating against as we calculate the actual spring load on the suspension. So let's go down to the private section and add this. All right, and I'll just include some notes here so you can kind of get an idea of why things are. So we've got the max length, so this is the distance, and everything's in Unreal Engine is calculated in centimeters. So when we're talking about length and distance, the unit that Unreal Engine uses is centimeters, so everything is just calculated against that. Compression damping, so this is the limit compression speed. This is the rebound damping, so this is the rebound speed. So we need to be able to check both compression and rebound. And then we have the resting force. This is the force that the vehicle will be. This is the force that's going to be keeping this, the vehicle up level with the road or with the surface that it's on. All right, after that, I'm going to be adding some additional data here, which is the displacement input, last displacement input. So we want to be able to track what it currently is and what it last was. This is going to help with calculating where we need to put the spring. Again, everything is calculated through delta seconds, so we need to know the last position before we move to the next position. We're also going to need, okay, so we already have the local offset, but we're also going to need spring displacement. And then finally, I'm going to be adding some variables in here for the smoothing. So if you want to do add suspension smoothing in there. So again, we've got the last length, the average count, and the average numbering. So again, this is where we can try and work on blending that information together to create a smoother suspension based on our calculations. All right, so this is all the private data that we're going to be used to calculate a spring or a suspension spring. All right, so I'm going to come back up to our public, up to the public section, and I'm going to add some more functions that we're going to need. And these are going to be some private functions that we're going to need to help with, well, not private functions, but these are functions that will allow us access to the private variables down here that we're calculating. So these are all going to be getters and setters for these private variables. So I'm just going to just bring them in as a block. So as you can see here, these are the getters. And here are our setters for our private variables. And I'm also going to create an initialization function. I'm going to just add the init function up here. So we are going to need to do a little initialization when we create this thing. So I'm going to move up here and I'm going to go into the suspension constructor and I'm going to add the init function so it can get called right in here. So when we create a new struct, we'll automatically run this initializer. All right, so now that we've got all of this set up, let's go ahead and work on the implementation pieces. So as you can see here, we've got a couple of green squigglies. A lot of this is inlined, but we do have some functions where I'm going to need to go to the implementation file to kind of, tease them out a little bit. So I'm going to start with set suspension length. So let's see if this puts it in the right place. Alright, looks like it's going to put it in the right place. So again, this is our tracing stuff. I'm just going to minimize this, and let's go ahead and bring in the code for our set suspension length. Alright. Alright, so this is how we're going to be setting up our suspension length based on a length value that's going to be coming in and a wheel radius. So, and we'll see this when we start getting into creating the setups. So this is, so we are going to, these are our internal private functions, our displacement input. So what we're going to do is we're going to take the length minus the raycast safety margin minus the wheel radius, right? And that's going to get our displacement input. Then we're going to take the displacement input and then we're going to do a max between 0 and whatever the input is. So if it's, whichever is greater, we're going to take, right? So we definitely don't want a negative displacement input. And then we need the spring displacement. So this is going to be the max length. Again, it's an internal variable minus the displacement input. So that should get us the actual suspension length. All right, so next, let's see what we got next. We've already got set velocity, set the local offset. Oops, I got 2 of these, so let me just remove that. We only need 1. So we got set that one, we got set local velocity, we've got the set local resting place. So let's do the update world raycast location. And again, this is something that needs to be done every time on every physics tick. So what we're going to be doing is we're going to be we're going to do our calculations. Well, first we're going to update the world location, resting location for each spring within the suspension system, right? And then from that, that's what we're going to then use to create our start trace and our end trace for our trace. Because again, remember, these wheels are going to be moving up and down on the Z location. So every time we calculate, and we're going to then say, okay, we're going to be moving this thing up, we're going to move this thing down. On the next tick, we have to reset the raycast to that new location. So that's what this function is going to help us do. So it's going to take the transform body. So this is the transform coming in. This is our wheel radius, which is what we're going to be using to calculate where we need the end trace to be. And then this is the suspension tracing output. So we created this structure, and again, this structure is on each and every wheel that we're going to be calculating this on. So, and then this is the output trace. So again, we're going to take the suspension axis. So this is the direction that we want the suspension to go in. So most likely it's going to be up or down. More traditionally, it's up or down. Maybe a little bit later, you might want to get a little bit crazy and maybe put a little bit of an angle in there if you wanted to do that. But for now, we're just going to use more traditional up-down direction. Then we need the world location. And so we're going to say get the resting position, and then we're going to take that resting position, and then we're going to take a look at the body transform position, and then that should get us the world location. And then get in the direction, and this is the world direction. So this is important because all of this needs to be in relationship to the actual vehicle, where it is in the world and the angle and the direction that it might be in. So if the vehicle is suddenly on its side, well, then we need to rotate everything to make sure the suspension system is still going to go in the right direction. And then finally, we're going to go ahead and create our start trace and end trace. So that's going to be the world location minus the world direction. And then that's going to be, well, first we're going to take the suspension max rise plus the safety margin. And then we just take, multiply that by this, and then we subtract that. So And this is just order of operations. So again, parentheses first, then multiplicative, and then add and subtract. And then ntrace, again, it's take this suspension. So this is max rise. So this is how far it can go up, right? And then this is max drop. This is how far it can go down. And this is based on the wheel radius. So max rise is on the safety margin. Drop is on the wheel radius. So we're going to do that. We're then going to multiply that by the world direction. And then after we've got that, then we're going to add the world location to it. So start trace is minus, end trace is plus. All right, so that, and again, this is going to, we'll see this being done on every physics tick of the simulations, because that wheel is going to be changing its location rather frequently. All right, so let's go back. Next up is going to be, let's see, we've got spring length. Oh, I got it in two places. Hang on, I got spring length. I need trace length. That's the one I meant to bring over. Yeah, that's the one I'm missing. So we have spring length in two places. What this one was meant to be is the get the trace length. That's what we want. So this is the trace length. So this is how far we're tracing. Good definition. And I'm just going to go ahead and put this in. So again, this is suspension max rise plus the safety margin, if you want to put any safety margin in, plus the suspension max drop, plus the wheel radius. So that's the actual length of that should be the actual length that we're going to be moving between, that our suspension system can move between as far as the trace. All right, and then we've got get spring length. Let's go ahead and just do this real quick. So here we've got suspension. So this is if we have suspension smoothing, we need to do some additional calculations through averaging, where if we don't have any suspension smoothing, suspension smoothing is set to 0, since this is in C++ we can kind of get away with this. So it's suspension smoothing is either 0 or it's somewhere between 1 and 10. So if we set suspension to smoothing to 0, in an if statement, it's almost like you're setting it to false. So then we're just going to take the spring displacement minus the max length. But anything more than that, anything if it's 1 or 10, between 1 and 10, suspension smoothing is technically turned on at that point. So then what we're going to then do is we're just going to take the displacement, and that's going to give us this new value here. And then we're going to take the averaging number based on how we're setting things up. So this is the averaging, suspension smoothing, and then we're going to increment this if we need to. Averaging length, averaging count. So the averaging length is this is our array, right? And then the averaging count is going to, if the averaging count is greater than or equal to the suspension smoothing, and then we're going to set the averaging count back to 0 again. And then we've got and then we go into this total. So we're going to set this total to 0. And then we're going to do a for loop here. So this is going to be, this is just simple little for loop using the int. So we just iterate through, increasing the total, and then from there we take the average plus the total divided by the average, and then that should give us the average. And so if we're using smoothing, we'll be returning the average of what we get through the smoothing algorithm here. Otherwise, we'll be using the displacement length here. All right, so now we're going to come to our last two functions. We're going to have simulate and the initializer. So Unreal Engine and Visual Studio aren't playing ball, so let's just go ahead and just bring them in manually. I'm going to start with the initializer first. So the initializer, so this is something that we need to do every time we set up a wheel. So we need to have some basic initialization. So as you can see here, we need to know the length and we need to know the suspension smoothing. So what this does is it's just going to go ahead and create that for us. So the length is just going to be it's going to be the suspension max rise and the suspension max drop. So again, rise is above the origin, drop is below, and this is based on, and this will be calculated based on the actual resting position. So as far as the max length, that's the maximum amount of travel your spring can go. So it can either go plus 10 up before it stops or plus 10 down. So that's our max length. And then suspension smoothing, again, it's going to take a look at the value being put in and it will clamp it between 0 and 10. That way, if we try and put 11, it'll just bring it back down to 10 again. All right. Okie doke. And then finally, we need to be able to simulate this on every tick, where, simulate our spring. All right. So as far as the simulation is concerned, it's going to take in a delta time here because everything's got to be done by by the frame rate, or the delta tick, I should say. This is actually going to be the physics tick. So we're going to take a look at, we're going to create a damping, and then what we're going to do is we're going to take the spring displacement, which is what we calculate, which is what we have here, minus the last displacement. So we need to know what the last position is. So if the spring displacement is less than the last displacement, then we are going to want to use compression damping, right? Versus if it's the other way around, we're going to want to use rebound damping instead. And then from there, this is the spring speed. All we're going to do is going to say the last displacement minus the spring displacement divided by delta time. So this is the speed of the spring. This is how it was going to react. And then then we're going to come down here, stiffness. So this is our spring stiffness force. So this is displacement multiplied by the spring rate. So that is this guy up here. This is the 250. So we're going to take the displacement multiplied by the spring rate. That's going to get us, that's the stiffness force. And then we have the damping force, which is the force which is going to be helping to kind of take that springiness out, right, over time, and that is going to be the spring speed, which we've calculated as displacement minus the displacement here divided by time. So this is the last displacement versus the current displacement, and so that's going to give us the spring speed multiplied by the damping. So this is compression or rebound damping, right? And then that's going to give us so then we have the stiffness force minus the damping force, and the whole idea is so that we can get that spring to come back to dampen it back down to 0 when the vehicle's fully stopped and idled. And then once we've got the suspension force, we're going to take the spring displacement and put that, which is the current spring displacement, and put that into the last displacement so that we're ready for when we get to the next tick. We now have this displacement value here. So again, this is happening on each tick. Based on what the last value is, we're going to be taking we'll be comparing that to the current value. All right, so I think that should do it for the struct that we need for our suspension. So I think we're in a good spot to let's go ahead and integrate that into our wheel class. And then from there, we'll start taking a look at adding the supporting structures around it before we integrate it into the simulation components. All right, so let's go find our wheel_vehicle.h file. So this is the U object. So this is actually an object that we're going to be using to simulate our carry all of our wheel code in. So as you can see here, we already have simulation set up for wheel profile, and we already have the suspension profile in here. So I think we're actually good for everything we need. as far as integrating this struct into here. So this is, again, the setups are going to be part of the wheel, and the nice thing about this is that I can now blueprint wheels, and we can then go ahead and set up the wheel profile and the suspension profile within that wheel. So that's kind of what we're going to do here. Let me just double check to see if there's anything we are missing. No, I think we actually have everything, because we needed a lot of this for the output information, so I think we're good now. Let's just go and take a look at the functions, just to see, just to make sure that they're properly implemented, and then we can probably move on to the wheel state that we need to be managing. Alright, let's take a peek. So in the CCP file, or CPP file, nope, looks like everything's wired up. So we did this in a previous video, so we've wired everything up. So this is the output data that we need to drive the animations, and then based on the animation data and where it gets put, we then need to then pipe that back into our wheel simulations for suspension. Alright, so we don't need to do anything here, so let's go ahead and move next over to our state. So we are going to need to track the actual wheel state. Again, we're going to have multiple wheels. We need to know what the state is of each of these wheels during the simulation. So to do that, we need to go and find our... Let's see, it is in movement traits. All right, so this is our simulation state. So just like we did for our direction state, right? So what I'm going to do is I'm just going to create a new struct, and I'm going to put it above the wheel simulation or the vehicle simulation state. So when we compile it, it all kind of links together nicely. So I'm just going to go ahead and just going to go and pull this in, since it's a rather large object, and then we can kind of bring it in pieces and kind of talk about it. So alright, so again, this is the physics wheel state, and we'll be adding that into the wheel simulation state to keep all of our state data together. So first off, like anything, we need some constructors, and we're going to have a couple of them. So we've got the generic constructor and destructor. I'm also going to add an additional overloaded additional set of constructors. So we've got this one, which is going to take in the physics wheel state and put it in, and then we've got this other one here, which is a reference using this operator constructor instead. And we'll go ahead and define those shortly. We're going to need an initializer, so whenever we create this wheel state, we need to know that, based on the number of wheels which we're tracking, we need to be able to initialize this. And our state object needs to be updated in multiple locations, so this is pretty lengthy, so I'll just kind of park it here. So we've got GT state, and then we actually have two functions on the PT. I think we only need to use one, but we'll keep the other one in here. But as you can see, we've got update GT, which is going to take the index, the offset, and the body instance, since the game thread uses the body instance target, where the PT state will take the wheel index, the offset, and the chaos rigid body handle internal. So this is the internal handle that it uses in the physics engine. And then we also have this second one, which is also going to use the physics handle, but we're also going to be adding the contact point if we need to use a contact point, as well as the surface handle. I think for this is usually, I think, used for if we're needing to update on a Spherecast, but I think most of what we need is just handled here. And finally, I've got a helper function here, which is going to be our get velocity at point. All right, so these are all the functions we're going to be using, and we'll go ahead and fill those out once I've gotten the data points in. All right, so first two, pretty simple, number of wheels on the ground. So we need to track the number of wheels on the ground. If 0 wheels are on the ground, that means our vehicle is flying. Otherwise, if we have at least one wheel on the ground, we need to recalculate based on, our mass distribution based on that. And then we also need to know are all the wheels on the ground. So number all. And then we have some additional things that we're going to be tracking as arrays. So let's go ahead and start pulling those over. All right, so this is everything that we need to be tracking for our wheels, and so we need to know the local wheel location as well as the world wheel location. We are also going to be tracking the wheel velocity, world and local. You know what, just to keep things a little bit consistent, I'm just gonna, we'll do local first and world second. And then lastly, we've got the wheel suspension trace as well as the trace results. So again, this is all going to go into the state object so that we can move between there, so that we can move this between the functions and break things up a little bit more easily when we do the actual simulation. So we'll be, so this is our simulation trace. Again, we need to know this per wheel, and we need to know each one of these wheels locations, world location, velocity, and world velocity. We need to know each wheel's suspension trace and how it's set up, right? And then we need to know the trace results, which are our hit result here. So that is all the information that we're going to be tracking. All right, so let's go ahead and finish this off by setting up our constructors and our functions here. So I'm just going to go do this. Let's see. Nope. All right, so we're going to need to go and do this the old-fashioned way and put this into our function. All right, so let's just move over here, and I'm just going to go ahead and just bring these functions in one at a time. So first function is going to be the overloaded constructor. So here's our physics wheel state. So again, this is taking in actually the physics wheel, a pointer to another physics wheel state, and it's just copying the data over that way. We have the operator version. So we'll just go ahead and do this as well. Again, this is taking physics wheel state on the operator constants. Again, it does the same thing. The only difference is first we need to check to see if this guy is valid. If it's not valid, if this is not a valid pointer, we'll dump out. Otherwise, if it is, then we'll go ahead and go and copy that information over and then return the pointer back. We have our initializer right here, so let's go ahead and do that real quick. Just going to go ahead. So our initializer, we've got, again, so each one of these is an array. So what we need to do is we're going to just dimension the array, pre-dimension that array. Again, because, so that we can synchronize everything. So everything that we're doing in our physics system, whether it be wings, thrusters, wheels, right, we need to be able to synchronize the setup structures from the actual wheels, and especially here where I actually have an instance of the wheel, which is going to be an object, and then I have the structure, which is going to be telling us, which of these objects we want to instant. But we need to be able to link those together. So, and so we need to just keep these synchronized. So once we've initialized everything, we should know what the number is. We should then be able to put it. So wheel number 1 in the setup should match wheel number 1 in the instanced. Wheel number 2 in the setup should match wheel number 2, and we'll just be able to find it in the array. So we're just presetting these arrays. That way we don't have to worry about add. We can just do that through this initializer. And these are arrays of vectors. We're just going to initialize the vectors to 0 through this array initialization function. So as you can see here, that's the element. So all of the elements are going to be set to 0, and we can put in the number of elements that we want this array, the size of the array. So that's what's being done there. And then with the wheel suspension tracing, we're just going to go ahead and just increase this by the number. There is no preset here that we need to do. All right, so that's the initializer. Let's see. And then I think we just need the other function. So I'm going to bring in the get velocity at point. So I'm just going to bring this one in first. So get velocity at point, I think we've seen this before when we were doing aircraft wings. It's the same idea. It's just using we're just going to get the world position of the rigid body, and we're going to then do a diff between the vector on the in point minus the center of mass, or center of mass of the world position. That'll get us a difference, and then we have the velocity minus the cross product of the difference and the I've forgotten what W is. It's not. I think that this is the inertia. W is the inertia. All right, but that should give us that should return a vector, which is the velocity at a specific point, and that point is going to be the point of our wheel. All right, so now we can come into the last three functions, which are going to be our update state GT, PT, and PT overloaded. All right, so GT. So this is us updating this information on the game thread. So when this is happening on the game thread, we're going to take the wheel index, we're going to take the offset, and we have the target instance. So again, we need to get we're going to get the transform, and this is the target instance. So on the target instance, there is a function through the pointer, since this is a coming through pointer reference, called get Unreal World Transform. So this will get us the Unreal version of the World Transform, which is our transform here. And then from that transform, what we're going to do is we're going to then get the transform position based off the offset. So here's the wheel location. So this is relative location. So this is the movement that we're doing relative. This is actually the world location, so we need the transform position, and we're going to move that by we're going to update that by the offset. Then we have the velocity, which is so again on the target instance there's a function called get Unreal World Velocity at point, and what we're going to do is we're going to take the world wheel location again by the index that it's on, so we're again referencing our wheel, and we're going to pipe that in to get the velocity at the local velocity, and then we also want to get the wheel velocity by using the world transform dot inverse transform vector, and again this will be this is the world velocity. Right. Yep, no. So this is the world wheel velocity location, and this is the local velocity location. All right. So then after this, let's go ahead and do the physics thread. So the physics thread here, it's very similar. The only difference is that we don't have a transform, so we need to create a transform. So, and we can create a transform by just taking the rotation and the vehicle handle. So X is always going to be the location, R on the vehicle handle is always going to be the rotation. Again, same idea, same calculations that is being done on the GT. The only difference is we just have to create a transform a little differently from the vehicle handle. And then if we're going to, if we need to also have to factor in the surface handle, we can do that through this function here. So again, we're just adding some additional things on. So this is the contact point and this is the surface handle. So again, this is so if we have a surface handle, right, then we can then say get velocity at points. This is the surface handle and the contact point, and that will give us the surface velocity, and then we can use the surface velocity in our calculation on the world wheel velocity here. And we just go ahead and take the location minus the surface velocity if we need to calculate that information. So it's just an expanded version, and this is happening on the physics thread because this is where we're going to be doing our suspension simulation. All right, so I think that should do it for all of the implementation. So I think we can just go ahead now and take our physics wheel state and put that into our vehicle state so that we can update and use that within our simulation. All right, so let's scroll on down. Let's see, I've got current gear here, so I'm just going to keep these two together. So I'm just going to put this above that. So here's our physics wheel state, so I'm just going to put that there. So again, it's just a property. It's got its own update functions, so we'll be updating this independently of updating all this other information. So we're continuing to update the vehicle, but because the wheels are considered kind of like appendages on the vehicle, we need to update those separately, and that's where we're going to be doing that there. All right, so I think that should do it for now. I don't think there's anything else we need to be adding in here. I'm just going to do a quick little double check. No, I think we're good. All right, so now that we've got the state object done, so we've got the simulation component for suspension, we've verified that it's integrated into the wheel class, so that's good. Now we've updated the state information. I think we're now ready to move over to our vehicle simulation component and then start integrating the setup for our suspension there. All right. All right, so simulation code. Okay, I think what I'm going to do is I'm actually going to stop this video right here. It's kind of getting on to almost an hour-long video, and I'm going to break this video into two parts. So I'm going to stop here on part one. I think it's a good place to stop before we get into the vehicle simulation, so we can create another video and really dedicate our time to kind of diving into this a little bit deeper in the integration of our suspension system, and then from there we should then be able to finish it off by bringing out the creating our wheel assets, setting it up, and hopefully seeing our vehicle bouncing at least bouncing around on the ground. So again, so yeah, I'm gonna just stop it right here. So if you like what I'm doing, feel free to subscribe to my channel and like my videos. Yeah, I'll see you in the next video. Cheers. Bye.